Welcome to session number 10. We're going to start talking about soils, and there will be probably 2-3 sessions dedicated to soils. Now, many people and farmers alike think that when they do a soil analysis, it's tell them everything that there is to be known about their soil. Well, this is really far from the truth, because the analysis sheet only tells them the relevant information that they need to have in order to be able to grow a crop successfully. The soil is made of so many things, and not all of them actually are important for the grower to know if he's going to make decisions about what to do. But let's talk about these things, briefly, just very briefly. Now, don't take this as a gospel because it varies a lot, okay? But an average fertile soil will have the following components in this percentage by volume, not by weight. About 45% mineral fraction, 25% air, 25% moisture. Now those two interchange, of course, because if you have more water, then more air is kicked out, of course, so the amount of air gets less. The other 5% OM stands for organic matter. Now this mineral component comes from rock, because soils come from rocks. When rocks break down by weathering, by natural process, by wind, moisture, etc., they crumble and, break down into smaller particles and smaller and smaller and smaller. Now the particles found in the soil are called sand, silt, and clay. Now this is a classification that is based on particle size and particle size only. It doesn't tell me much about the chemistry of that soil. So when someone tells me, oh, I've got a clayey soil, it really doesn't tell me much. It tells me a lot about its texture, about its water penetration capacity, water holding capacity, but it doesn't tell me much about how rich or poor that soil is. More about that later on. Now, what about the weight? This classification, we said, is based on weight. Now, this is the heaviest component of the soil, okay? And anyway, when you do a soil analysis, you have to dry it first, so you get rid of all the water. So when you have a dry soil sample, it's virtually like all, with the little bit coming from organic matter, it's virtually all mineral component. Now, on an average, again, this depends on the texture of the soil, but on average, a hectare of soil has 2,000 tons in the topsoil. What's the topsoil? The top 20-25 centimeters. And when we go from metric to imperial, actually, this is an easy, transformation here. Because 2,000 kilogram per hectare is almost exactly identical to 2 million pounds per acre. So the conversion here is very easy. Now, so let's keep that figure in mind. That's a hell of an amount, 2,000 tons. So 1% of this, only 1% is 20,000 kilogram per hectare. 20 tons per hectare. So if you have 1% of something in your soil, you have 20 tons of it per hectare. Wait till you hear how much aluminium you can have in your soil. The total amount of aluminium in a soil varies from about 1% to about 30%. So if we're talking about 30%, you have to multiply this figure by 30, and you end up with 600,000 kilograms of aluminium per hectare. Oh, how come we're not all dead? Well, luckily, this aluminium is not in a form that is in solution. It is held in particles, bigger particles. Sometimes it's held in substances that are quite inert, and most people are familiar with the term bauxite. This is where aluminium is extracted from. That's the aluminium ore, bauxite. But a lot of soils don't have bauxite, and they still have high amounts of aluminium. And that aluminium is in a form that is extremely essential for production, for growing crops. Why? Because it is the center of units referred to as aluminosilicates. And that's a huge array of complex substances that are made primarily of sheets of silica and alumina. And when the aluminium gets leached out and weathered out over the years, again by moisture and air and all sort of things, it creates a negative charge on the clay particle, which enables it to hold nutrients and prevent leaching. I'll explain more about that later on. But if you really want a thorough explanation of this, I can provide in the question section below. I don't want to add this to the session to make it too long and too complex. So you've got the rock, which is the parent material. It gets broken down physically into smaller particles. So that's physical breakdown. And then, especially in the clay fraction, you get this chemical weathering that is creating a negatively charged particle. And you end up with a whole array of substances, a lot of them you're familiar with. If I mention some names, you'll say, now I know what you're talking about. How about the word vermiculite? Vermiculite is used intensely in the nursery industry. They don't get it in a clay form, but never mind the physical structure. Vermiculite is one of those aluminosilicate minerals that has a high cation exchange, good water holding capacity, and it's an excellent medium to grow plants in, to give them a good kickstart. I'll just mention a few other names just to satisfy your curiosity. Bentonite, muscovite, montmorillonite, kaolinite, zeolite. They're all, and those of you who used to read Superman, kryptonite is not one of them. Okay? So these are very essential compounds that are present in the soil and that give the particle, the clay particle. Why are we talking mainly about the clay? Because the clay particles have the highest surface area. Certainly this is common sense. You know, if you take a particle, you break it down into two, then the total surface area of both is more than the individual one. And then if you keep breaking it down more and more and more, the clay particle will have the highest surface area. So the surface area of a clay will have a negative charge. Now this will attract those essential elements, the ones that are positively charged, and most of them are. You know, things like potassium, calcium, magnesium, and the trace elements, of course, copper, zinc, manganese, iron, zinc, they're all positively charged particles. So these will get attracted to this, like, I wouldn't say like glue, but like electrostatically attracted. They're not very firmly bound, so the root can come here and take them. So they're called available. They're referred to as available. Unlike the ones that are loose in solution. You see, these ones here, they're swimming in solution. They are available, but there's nothing to hold them. They don't have a safety net. If you flush this, if you have this soil in a cup with a hole in the bottom or in a pot, and you drench it with water, these things will get leached out and they will be lost. Now, sometimes we need to do this to get rid of harmful salts, you know, sodium and chloride, but you don't want to leach out the essential elements. So this feature here is called cation exchange, cation exchange. And the ability to hold cations by the soil is called the cation exchange capacity. And the interesting thing here is these sites are renewable, you know, reusable, you know. So let's say the root will take this magnesium here, and this site becomes vacant. Well, this calcium can come and jump and take it. So once it's there, it's there. You know, you can't get rid of it. So that's a very important feature that explains the ability of soils to hold nutrients. Now, organic matter has the same feature, but there are problems, again, with organic matter, as we shall talk about later on. Now, how do we make sure, by the way, that this aluminium, this huge amount of aluminium, does not get into solution. There's a simple way to do it, a way that most people are not really aware of, especially home gardeners. pH. Control the pH. If you don't want this aluminium to be solubilized and become toxic for you and your children and your chooks and goats, whatever, make sure that your pH is definitely above 5, preferably in the 6 mark, because the lower the pH, the higher the aluminium solubility is. Now, believe it or not, many organic growers are not aware of that. They're not told that they need to apply a lot of lime to make sure that the soils have good pHs and that the aluminium does not accumulate in that crop. Now, does it mean that they all don't do it? No, that's not what I'm saying. There's a lot of good things to organic growing and to the whole idea, and I'm going to be talking about them because fair is fair. But when there is a flaw in the system, we need to be aware of it, so we educate each other. And if we are going to be growing things and we believe that we're going to be doing them organically, we have to do them also in a responsible way. Because remember here, we are growing for food, our own food. We're not even just taking it to the market to sell it. We want to grow healthy, nutritious food that is highest in minerals and lowest in toxic minerals. Well, that's all for now. Thank you for listening.